Good morning. My name is Tracy Reddig, and welcome to American Iron and Steel Institute's virtual event, a review of liquid metal embrittlement from our Auto Steel partnership. At this time, I'd like to introduce John Catterall, Vice President, Automotive Program for AISI. John?
Thank you, Tracy, and welcome everybody this morning. I'd like to introduce our guest presenter today, Dr. Mike Karagoulis, a Master Mechanic of Welding Development at General Motors. Mike has devoted his career to the study and appointment and improvement of resistance welding. He is known for significant work in fuel tank seam welding, early development and rollout of the weld verification process used in vehicle launch programs at General Motors, refinement and standardization of tip dressing, several new electrode designs, a thermal approach to optimizing spot weld nugget growth, and for industry leadership regarding welding of third generation steels. Those are just a few things that Mike has worked on over his career. He has been with General Motors for 29 years now. I actually had the pleasure of working with Mike for a number of years when I was at General Motors. He holds 2 degrees in metallurgy engineering from the University of Michigan and 1 from Michigan State University. He is a recognized industrial leader in welding and joining, holding 29 US patents and 2 GM Boss Kettering Awards. In 2018, he received the Elihu Thomas Award for Resistance Welding Innovation from the Resistance Welding Manufacturing Alliance. And in 2020, he became a Fellow of the American Welding Society. And now we will hear from Mike Karagoulis on a review of LME, how LME can impact various weld types across a variety of materials. So welcome, Mike.
Thank you, John. Thank you, Tracy. Hello, everybody. We're going to talk about LME cracking in the automotive applications. Okay, so LME doesn't get talked about a lot, but lately it has been, and these pictures will show you why. Let's look at what LME cracks might look like in a resistance spot weld. They can be on the edge, they can be some other locations, but this is the, let's say, the most alarming location for a crack in a weld. All your loads come through the edges, right? So if that's not, well, we don't want that crack. Let's say, as an automaker, I don't want that crack. We found a way to turn that crack on in gas metal arc welding, so it could happen there. And even in drawn arc welding, where you put these studs all over the car, if you flip the panel over, this is the back side of this sheet down here, you can see that there's cracks in the peripheral direction and also radially extending outwards. So anyway, we can't ignore these cracks, and that's what this talk is about. The cause of LME is, let's say, the instantaneous preferential dissolution of the grain boundaries in the steel, and it requires 3 things to be present. You need tensile strain, you need a foreign liquid metal such as zinc, or maybe even lead. We don't put lead on steel cars anymore, but we did put it on fuel tanks, so that's my first exposure to it. And then a susceptible microstructure. So if you have all 3 of these things simultaneously, you have this common area in the center where you may get LME. Here's a picture somebody made of an LME crack, and you can see the zinc running into the material. But it is something that happens very, very, very quickly when you have the correct magic conditions to, if they're all switched on. Okay, here's a little metallurgy. John told you I was a metallurgist, so here's your the obligatory phase diagram. This case, it's iron zinc. Our foreign liquid is zinc on the surface of the iron, and we are dealing with 2 drastically different melting points. Okay, steel is up in the neighborhood of 1500 C, zinc down in the neighborhood of 400 C. So you have all this temperature here where you might have liquid metal present. However, there is one thing in our favor, and that's the boiling point of zinc, which is at around 900. So you don't tend to see liquid metal embrittlement above 900 C because it just disappears unless it's trapped in, like underneath the electrode. There's no air. I mean, it's a high pressure area, so you might have zinc there. But anything that's open to the surface would be gone by the time you get in the neighborhood of 900 C. So our general zone of concern is from 400 to 900. Okay, so why are we interested in LME in the car business? Well, this temperature range, 400 to 900 C, is a temperature range you can't avoid in most steel welding processes, assuming it's fusion welding, which means we're melting an actual nugget or a weld bead or something like that. We're at that melting point, 1500. And then far away from the weld, we're back down at the base metal temperature. So we have every temperature in between 1500 and room temperature on that part somewhere. So somewhere we're going to be in this temperature regime where we have to think about LME. So that means that one of those bubbles in the Venn diagram, the liquid metal bubble, is going to be switched on. So do we have the other two conditions, namely the tensile strain and the susceptible microstructure? If all three are on, then you can possibly have LME. We've all seen this banana chart showing the elongation and tensile strength of steels. And what I did was I added a new bubble on here for where we tend to see LME. It's not very scientific. These are just where I personally have observed LME. I've not observed it in these materials here, and I've not observed it in martensite and PHS, but really, when you get above 800 megapascals, that's when you start to see it happening at lower and lower temperatures. Okay, so how do you tackle this nasty problem? A lot of people are doing a lot of things. What I wanted to see was kind of an old problem-solving trick. I can't remember the name of it, so I'm sorry, but it has to do with Taguchi and other, statistical methods. And it says basically, if you can turn a problem on and you can turn a problem off, then you obviously know something about the problem. And you could get really academic on how sensitive the microstructure is and what's going on at the metal surface and all these kind of things. But if you can just turn the problem on and turn the problem off, you've learned something. So that's what this practical approach involves. So we developed laboratory procedures in order to activate LME according to this Venn diagram. Now, we, when as an automaker, we don't make steel. We use steel, so we don't control the microstructure. Others do that. But if we can develop a procedure where we control the temperature on the surface, that produces the liquid metal, and we can control the tensile strain, then we can kind of evaluate the size of this overlapping area. That's the theory here, okay? And then if we're successful at that, then we leave it up to others to maybe turn off LME. What could you do? You could modify the chemistry of the steel. You could modify the heat treatment or the microstructure of the steel. You could modify the coating. You could even modify welding. But like I showed you a couple slides ago, that temperature range is 400 to 900 C. That's the heat affected zone. So you're going to have a heat affected zone if you're welding with fusion, any of the fusion methods. Okay, so we decided, we all know spot welding has a lot of variation in it. It just kind of goes with the process. We'll get into that in a minute. But in order to study just LME and get away from the welding variables, we decided to use hot tensile testing. Okay, the machine that does that's called a Gleeble tester. They have one at Ohio State, and ASP sponsored a project to examine whether you get LME at different strain rates. Okay, tensile strain is one of the inputs. One of the bubbles on the Venn diagram. The other one is temperature causing the liquid metal. So we have this XY space that we did a lot of hot tensile testing. Okay, so what does LME look like in a hot tensile test? This tensile sample here shows a lot of cracking in the sample, and that indicates the material's falling apart. If this same batch of material was stripped of the zinc, you just do a quick acid treatment and dissolve off the zinc, then these cracks go away and you have a nice hot taffy pull, you know, with a lot of necking and so on, and you don't see any of these cracks. So it's pretty easy to look at the sample and observe whether you had LME or not. So that's the qualitative answer. There is a quantitative answer. Sorry, it does change the ductility level, how much stretch you get. If there's no LME, then you have more of a taffy sample when you're pulling it at this elevated temperature, so you're going to see more ductility. So for this ASP project at Ohio State, we tested a range of body materials, and the results really spoke volumes to me. Most of the materials that we build the car out of and have for decades fell in this upper temperature group. So in other words, if you, let's pick one of these lines, like the red one here. That happens to be DP600 material. So this line defines the boundary between where LME is occurring and where LME stops occurring. Okay, and this is called deep LME. It's not shallow superficial stuff. It's actual deep cracks opening up in the material. So this is the trigger point for that material. And so most of these body materials fell in this same general temperature range of 650 to 750 or so centigrade. Then comes along the Gen 3 materials, and they're cracking 500 to less than 600. And the slope of these lines in the Gen 3 is backwards. You would think that if you pulled the sample at a slower temperature that you might stave off LME and it might happen at an even higher temperature than low. So here you've got a negative slope on the lines, okay? That's intuitive to me. Then Gen 3 comes along and it's sloped backwards. So there's clearly some other mechanism going on here. That's a very academic thing. And, we're not getting into that here because we're just trying to turn the problem on, trying to turn the problem off. And we'll let the universities and the real academicians study what's going on in the grain boundaries, et cetera. So the startling conclusion here is that you have low temperature LME, which we don't like, high temperature LME, which has been around for decades and doesn't really manifest itself very much in auto bodies. Okay, so that's the conclusion for Gleeble testing. Now we'd like to go back to welding. Can we turn on the LME reaction using a spot welder? Okay, here's my old sketch of what's going on with a spot weld. You got electrodes, you got your sheet metal, and you're making a nugget there based on current and resistance and so on. It's the Joule effect. Okay, so we're heating the material. If it's part of the nugget, it's going to be at 1500 C or thereabouts. And then far, far away, we're going to be at room temperature. And so we have all the temperatures in between there. So where are we going to see the crack? So what we want to do is try to create a scenario where we have the same temperature and strain conditions of the Gleeble hot tensile test, but we're going to do it with a spot welder. So the first challenge is to create tensile strain. When we're pushing on the sample, we're putting it in compression. Where's the tension? So we'll talk about that. Secondly, how are we going to get to the same activation temperature that we observed in the Gleeble test? Okay, activation temperature, let's say it's the Gen 3 here, strain rate of 100 millimeters per second, and we're trying to get to 530 degrees, something like that. So how do we do that with a spot welder? How do we control the temperature of the heat affected zone? And then thirdly is repeatability. Did I say we have repeatability issues in spot welding? Current density is not constant. Force and the pressure on the tip face is not constant. And then there's this ugly thing called expulsion that when it happens, it throws all the parameters off momentarily. So we got to deal with that. Where do cracks occur? We have relatively cleanly developed 4 types of cracks, A, B, C, D, based on where they're occurring. A is underneath the electrode imprint. So anywhere in this, we call it a 6 millimeter face diameter. That's kind of a common industry standard. So type A is under the electrode. Type B is decidedly not under the electrode. So it's off to one side or another, and it's away from the electrode imprint and also that outer transition imprint. When there's indentation of the electrode, more and more of the electrode begins to contact the metal. Okay, so it's a little different in this intermediate transition space than saying, okay, type B is where it never ever touched the electrode at any point during the weld process. Okay, and then type C is when it cracks in between the sheets. This is reasonably rare, but maybe it's rare because it's hard to find, because it's not visible unless you actually section the sample and get lucky. That's when we've seen it. You could x-ray it, maybe find it that way, but anyway, in this particular spot weld test, we don't see C very often. Type D is in that no man's land between the electrode face and the undisturbed original surface. So it's that region that only touches the electrode during the act of indentation. Okay, so A, B, C, D. Now, the 2 cracks that are most prevalent in this spot weld test ended up being type A and type B. Type A, you can see it's under the electrode. Type B is peripheral. Okay, you have these arms cracking radially, stemming off of the peripheral crack. That maybe is type E, I don't know, but its temperature is falling very quickly as you get further away, and this, moving away from the nugget. This is molten metal underneath here, and it's quickly, the temperature's falling like a rock as you're getting away from this. So the fact that this has a radial crack moving away from the temperature means it's happening. It's really susceptible at an extremely low temperature. So that's the most egregious LME crack as far as saying, hey, you have a sensitive microstructure. Okay, type B is the main detriment in car body welding because this is what it looks like when you section through one of these. It can be extremely deep. It could be full thickness of the sheet, and depending on the orientation of that, you can reduce the fatigue life up to 1.5 orders of magnitude. Okay, the blue line here is samples like these, which have the zinc removed, and so we know there's no weld cracking. So the zinc was stripped off, then it was welded, and we got this fatigue line. And then when we left the zinc there and did basically the same welds, we had cracks, and there was a big drop in fatigue life from 5 million down to less than 100,000. So type B is the one we would really like to turn off. So I'm pretty much just going to talk about type B here for the rest of the time. So how do we design a spot weld that maximizes the liquid metal, the temperature domain, and the tensile strain at the type B crack location? So we want to control the tensile strain and control the temperature, because that has to do with liquid metal. And then how do we suppress weld expulsion, because weld expulsion will cause you repeatability problems in any kind of crack making regimen. All right, so the first topic is how do we create tensile strains using applied compression. Has anybody ever seen the movie Free Willy? It was a while ago, almost 30 years, but at one point they pick up the whale in this sling and they free him from the captive pool and they put him back in the ocean, and that's a great moment during the movie. Whales are heavy and they're applying a compressive load, but it's held up by a sling, so that sling is in tension. Okay, so that's the model, is the sling. Okay, another manifestation of that is me in a hammock. When I lay in a hammock, I know that there's tension in the strings, and that's what's holding me up. And the tension can be quite high, depending on my diet and other things like that. So my weight is the weld force pushing down. Okay, the electrode is the weight, and it's kind of a hammock. Okay, if you look at the moment of indentation, you got this molten, squishy pudding underneath here, and it's squeezing out, which allows for indentation. And as that's going on, we're creating those hammock strains along the surface. Okay, if you had an initial point A and B on the parent metal surface, let's say there's a rope going across there, then when you indent, that rope has to get longer, right? Because now the shortest distance between 2 points is a straight line, but we've stretched it. So there's your tensile strain. And if you can get the tensile strain and getting the Gleeble temperature at that location, then you might have a good way to repeatably make a crack and study just the sensitivity of the microstructure. All right. So how do we get this area up to the magic temperature where the Gleeble tester said there was going to be a crack? A standard GM weld schedule for 1.6 millimeter sheet is in the neighborhood of 640 milliseconds. And we created a heat affected zone diameter of 8.5 millimeters. Okay, so the red line. We're obviously not up to temperature here. This one didn't crack. We want to warm that up more. The way to do that is with more time. More time allows the heat to go sideways in the weld. More current allows the nugget to go more toward the electrode. Okay, so current drives the nugget taller and time drives it sideways. So let's double the time. That's what we're doing here basically. And then when we did that, the heat affected zone diameter jumped up to 10.7 millimeters, and that gave us a suitable temperature for creating this crack. Okay, and you can see little superficial cracks beginning to form on the opposite side. So that's basically the strategy with parameters. Thirdly, we want to suppress expulsion. When you have expulsion, we have repeatability problems because there's chaos at the moment of expulsion. It could happen anywhere during the weld schedule, but at that particular moment when it happens, you have this molten metal leaking out. Current starts going through the molten pool that's frozen quickly. And anyway, current density changes. The resistance of the weld changes because now you have a shunt path, and then force changes because you just shot out a bunch of metal. The electrode has to advance, and until it does, you have this momentary flutter in all your main input parameters. So what we found is an effective way to suppress the expulsion is to use progressive sloping impulses. In other words, we have a whole bunch of pulses here. We're starting at a low current, and within each pulse we're using upslope, but it's progressive because the pulse 2 begins where pulse 1 left off in terms of current. So it's gradually going higher, 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 higher. Okay? So that technique allowed us to delay the time when expulsion occurs. So we have all of this crack development time down in the beginning of the weld schedule. All right, so I want to get right in and show you this in action. Here's two steels. They're both the same grade. They're just from different batches, maybe from different suppliers. It's all Gen 3 980 hot dip, and it's in the high elongation category. And they're nominally 1.5. Steel F is 1.4. 154 is 1.6. So let's put these side by side and apply this progressive sloping weld schedule at a low current. In this case, we're applying 7 kiloamps. Now, I said we're using upslope. So when I say 7 kiloamps, I mean that we're ending at 7 kiloamps. Every one of the welds I show you here is going to start at 5 kiloamps, and by the time it gets to the end of the 8th pulse, it'll be at 7 kiloamps. So we're just trying to gradually put in more and more current in order to warm this up and try and get that Gleeble condition out here at the where the B crack might form. Okay, so these two steels responded with a small nugget. They're not etched identically, but you can kind of see an outline of a heat affected zone. They're progressing at more or less the same rate, and no cracking. Okay, so now instead of stopping at 7 kiloamps, we'll turn up the furnace a little bit. Now we're going to stop at 7.5 kiloamps, and we drove a bigger nugget. You expect that. Still no LME in either material, so far so good. The third weld is at 8 kiloamps. This one is starting to show a little bit of superficial LME. This is a type A, this is a type B, and so if you look at the yellow trace here, which is current, we're just gradually warming that up. Let me briefly mention what these other traces are. The blue is the voltage between the tips. You can see what's going on with that, simultaneous to current. The green curve is the product of current times voltage, which all you weld engineers know, that's power. Current times voltage is power. And then if you take the ratio, voltage divided by current, then you have resistance, which is the pink. Okay? So that's what these traces are. 8.5 kiloamps. This guy made some little cracks at 8.0, and now they're getting deeper and more prevalent. This material on the right, still no cracks. Everything's calm and good. Okay, so roughly equal treatment is producing cracks in this material, but not in this material. So let's warm it up some more. So we go from 8.5 to 9.0. Now this crack is really starting to take off. And still no crack in this 154 material. Okay, so we're below expulsion. There isn't a hint of expulsion in this anywhere. I'll show you when it happens. You'll see it be pretty obvious. Okay, now at 9.5, cracks basically all the way through the material, and it's the fact that it's showing up on the other side means it's probably going all the way around. So this is the same crack as this. It's just, it's basically going all the way around. At 10.0, this material is consistently cracking. It's just more and more as you put more and more energy into it. This one still dead, no cracking. 10.5, okay, more of the same. You just have more indentation here. You see how this is well into the heat affected zone, and that same approximate temperature regime and indentation and everything is not producing the cracks in this material. There's something basically different. Okay, now the one on the left has a drop in the voltage curve at what is that? So either between the 5th and the 6th pulse, and that translates, if you look at the power curve, big drop in power there because it's the product of current times voltage. And that power drop probably signifies the end of nugget growth, okay, because at a lower power, your energy, well, your power by definition is less. Your nugget pretty much stops growing when that happens. Although, we are continuing to upslope, so it is trying to recover and resume. But if you look at, this is Weld at 11 kiloamps. If we go back to 10.5, see our peak power occurred on the last pulse. Here, our peak power is not so much the last pulse. It was also in the 5th pulse. But the Weld before, which was at lower current, actually finished at a higher power level. Pretty interesting. So anyway, when you have a sudden drop in power and in between the 5th and 6th pulse, and you have that force fluctuation, which I'm not even keeping track of here, but it just changed the whole crack formation mode, right? The crack is probably forming at this point in time, and it just didn't get a chance to make the type B crack because the type A crack preceded it and maybe relieve some of the strain or whatever, the stress. The one on the right is just still doing fine, no cracks. So this test continues. We don't stop at 11 kiloamps. We start at 7 kiloamps and we go up to 14.5. So every position on this x-axis represents a weld that was made at a particular current, as indicated. And if there's a crack, then there'll be a bar on here indicating that there's a crack. So this first one, we looked at this weld at 8.0, and it was about 10% of the material thickness. Then when we went up 500 amps, now it's 20% of the way through the thickness. At 9 kiloamps, it's 75% of the way through the thickness, and on and on. Okay, and then once it gets to full thickness, that's all it can be. When we got above expulsion at some point, we started to form the blue crack. Okay, I'm sorry, the colors here indicate the crack location, okay, which is the crack type. So B is the one, the nasty one we really don't want to see on a automotive vehicle. So that's the one we watch the most. The material on the right had no cracking below expulsion. Really nice thing to see. Above expulsion, we did see some cracking, but not the red type cracking. We only saw blue, which is type A, under the electrode, and then green, which is in that transition space between the electrode and the parent material that the electrode only touches during indentation. So these are the most friendly kinds of LME, and they're above the expulsion point. So hence we gave this a green and this one, or this material, a red. Okay, so we interpreted the results. We wrote a procedure for how to do this test. It's public domain, so you guys can access it, download it, use it, and we hope that you do. In the procedure, we have interpretation guide. We have the 4 types of cracks, and if it's below expulsion, we have one interpretation of whether we accept it, the crack, type A, B, C, or D. Above expulsion, we have the chaos factor, and so the accept reject criteria change a bit. But basically, we never want to see type B. Type C, you don't see very much, but if you do, it's not okay. Type D, if it's above expulsion, if it's shallow, that's understandable, acceptable. Type A, cracking will accept at any depth if it's above expulsion. Below expulsion, we only want to see superficial type A cracking. Okay? So, we tested, 14 steels, I think, here for ASP. And here's a different way of showing the graphical results in a table. So the columns represent amperage, and if there was a crack, there'll be something in the cell okay, and we denote the expulsion point. This first material was a 1 millimeter EG 980 material, lot number 161. It had expulsion at 9 kiloamps, and all the LME occurred above expulsion. A little bit of red, and the rest of it was blue. Okay, so that's how you interpret those results. We tested in the 980 world. We tested 2 thicknesses, 1.0, 1.6. Basically, we were looking for 1.0, 1.5, but you know, you test what they give you. So sometimes it's not 1.5, it'll be 1.6 or 1.4, whatever. And we had 3 different types of coatings: EG, GI. Well, EG is electrogalvanized, GI is the hot dip, and then GA is the galvanneal. So when we did all that, most of the tests had at least some amount of red cracking, except for 155 and 154, okay, which had no red cracking. There's something generally good about how that material is made, and it has a lower crack tendency than the others. Now, the pictures I showed you, the micrographs and the welding data that I showed you, was a comparison of this one, 154, and then this material F. Okay, so it was basically the best result right next to the worst result. You can see what that might mean. Okay, we also tested 1180 materials, and there, everything we tested had some amount of type B cracking, which is the red boxes here. And so I know everybody's working, the steel makers are working hard on their materials, so what you test this year might be different than the results you get next year, because people want to get this LME cracking under control. But anyway, having a nice metric for it gives everybody a common playing field to measure their progress in this area. Okay, so in conclusion, we developed a rapid LME screening test using spot welding. It was taking like a month to test a material using a Gleeble tester. I know some people can do it much quicker, but with students and down at OSU and, you know, solving problems with, you know, our argon purge and things like that, it ended up taking us a month to do a sample. And with the spot welding test, it's like a day to weld it and 2 days to do the metallography and write up a report and that kind of stuff. So went from 30 days to 3 days. So much quicker and low infrastructure, because now you don't need a Gleeble tester. You can just use a spot welder. Our results, that special weld schedule that I showed you was developed off of welding the same batches that we were tested on the Gleeble tester. And so we didn't stop tweaking the weld parameters until we got good correlation with the Gleeble results. Okay, so that was our goal, is to get the Gleeble result, the Cadillac result, at a Chevrolet price. Okay, there's my ad for GM. We tested a variety of Gen 3 materials, and the results showed a wide spectrum of LME sensitivity in the supply base. We've made this test procedure available to ASP members, and we're making it available beyond ASP because we think that's the right thing to do. We want the material supply fixed so that anybody building a car should be able to rely on these new materials and not be constantly looking over their shoulder for an LME problem. We tested the 3 types of zinc coatings, the common ones, the GI, it's a hot dip, electrogalvanized, EG, and then the galvanneal. There wasn't any slam dunk there that one's better than the other. All right, so we've taken and improved the speed of testing by having this rapid test procedure that almost anybody can do. If they're in the welding business, they have a spot welder, then that's pretty much all you need. So ASP member companies, test labs, universities, there's actually a number of folks using this method now and generating results. The steel makers are applying this procedure and developing LME resistant steels. So the material that we tested in 2019 was measurably better than the material we tested in 2018. And I think that there's a connection between using this test and not using it. So anybody's free to use the results for internal testing. And it's also, we weren't intending this, but because it's pretty repeatable at making cracks, the people that are studying LME cracks for mechanical testing, fatigue, CAE studies, etc., they are starting to use this method because it gives you a way to control the crack depth more accurately. What's going to happen in the future? Well, there's a need to continue testing new materials as they come along and improving the Gen 3 supply base. But also, we should probably be looking at anything above 800 megapascals and just checking it to see if LME is going to be a problem. As steel makers are tweaking chemistries and trying to get the strength level up, the ductility up, we should be looking at this. We don't think it needs to be looked at for HSLA or martensite. They appear to be pretty immune to the LME, type B LME. You can also use it to study different coating variables. There's a zinc coating called ZAM, zinc, aluminum, magnesium. You could see if that changes the LME sensitivity of the steel. Lots of things you could do with it. We can also explore on the user side the LME performance rating, and the big question is whether this susceptibility matters to a vehicle. Okay, in the weld lab, you're controlling all these variables. You got a crack. Does that mean that I'm going to get a crack when I make my Chevy? Well, that's a very good question. And so we have some amount of testing the best of the best and the worst of the worst, the Bob and the wow, as we call it, and putting it in harm's way as far as, okay, what if you have a big fit-up gap? What if you make an edge weld? What if you have these other disturbances? Does that cause LME suddenly to come back even in a good material? And then other spot weld configurations, maybe you're welding a thick to a thin, or maybe you're gas metal arc welding or laser welding. There's a lot of things that we have yet to look at. So those are part of the future plans. Okay, I think, yeah, I'm done with my slides. So I believe we can get webinar downloads from the AutoSteel website. And for more information, please contact Kevin Tang, who's going to replace me. This is my last week of working. John said I was working for 29 years. I've worked for 39 years. And this is my last week. So this is, anyway, in the future, please talk to Kevin. He's also a metallurgist, and he's been looking over my shoulder for the last 4 years. So he's ready for the challenge. Hassan is also a extremely valuable team member from the steel company side. He knows a lot about LME, and he's our team leader, so he's equally ready to help. Eric McCarty is our project manager at ASP. Okay, I think we can throw this open to questions, and I'm pretty much gave my whole story here.
So good morning, Mike. This is Eric. I do have a list of questions for you, probably about 9 in total. I'll start off with the first one here. Yep. The first one was asked some time ago during your presentation, and he asked, this came from Richard. Richard asked, is Fatigue life reduction of up to 1.5 times. Was that the most severe cracking case?
Yeah, I'm going back to that slide for us. Here we go. Fatigue life. This is what I call flange tension. Each one of these samples here is 2 tensile bars that were spot welded in the gauge section. So there's a second piece underneath this one that you see, and we pull this is the width of a typical weld flange, like let's say a roof rail or something like that. And if you did roof crush, you'd be putting the roof in this type of tensile load. So yeah, this is having this crack that you see here and having it oriented directly in the load path has the greatest effect.
All right, have a second question also from Richard. Asked, in your comparison between lots F and lot 154, which has different thicknesses, do you have a different starting current?
No, we validated when we developed these parameters that you see here. We tested that range from it's 1.5 plus or minus 1/10 of a millimeter, and then there's no need to change the parameters. When you go to 1.0, we did have to change the parameters. So instead of 8 pulses on the thin material, we used 11 pulses. And it's interesting because we want to have a similar heat affected zone diameter, but we're going to do it in a thinner sheet. When we weld the 1.0, we still have to get the heat affected zone to push out roughly the same distance. So the overall time, this is 1320, in the 1 millimeter material, the overall time is roughly the same because that's how long it takes heat to travel sideways to that diameter we're trying to hit. This is 10, 11 millimeters of heat affected zone. So yes, there is an effect of thickness on these parameters, but we've boxed that into 2 thickness ranges, nominally 1.1 plus or minus 0.1, and then 1.5 plus or minus 0.1. And we got good correlation with the way the procedure is written for that entire range of thickness. So yeah, it didn't really affect the results that I showed you. The fact that one was 1.4, the other was 1.6. You can see the nuggets roughly within striking distance, whether it's the material on the left or the material on the right. Okay.
Okay, so just as a follow-on to this question, and you kind of covered it, but it might be a little bit more specifically, does the difference in thickness affect the start of LME?
In a Gleeble test, I'm pretty sure the answer is no, because it's strictly a matter of, did you meet the conditions? Where was it? Where'd it go? There it is. All right. I'm not even showing thickness on this chart because I think that if you have the temperature and the strain rate that turns on LME, it doesn't matter how thick the substrate is. When you take this result and you apply it to spot welding, now you have to think about whether you created the same conditions to make this type B crack in a thin sheet or a thick sheet. It's going to affect it. But if you hit that same point that the Gleeble test is predicting the initiation of LME, I think that initiation point is not dependent on the thickness. It's just a matter of whether your weld parameters simulated that Gleeble test condition. Okay, so that's why we have a different setup for the different thicknesses. Could we develop more? Yeah, we could for intermediate thicknesses. We intended to do a weld parameter test for 2.0, but the steel companies are just now beginning to make material in that thickness range. So we had no material to work from. But yeah, call that future work. Even the modelers can help us there and just say, okay, if this weld schedule is giving you a where'd it go? Yeah, if this weld schedule gives you this heat pattern, and this weld schedule gives you a wider heat pattern, what is the optimum heat pattern? There's a modeling answer there that I haven't seen. So maybe those folks can help us.
So I have two related questions here. I'll ask the first one. Is there a difference between the different coatings in terms of LME performance?
Well, let's see. Where's the graph? Here's the table. You can see a couple of EGs and then some GIs, and here's another GI. Clearly, if you look at these GIs, GI is the most common in North America. There's good GI and then there's bad GI. Was that the coating? I don't know. I can't really know that with my test, but maybe the steelmaker knows if these GIs are different from each other. But boy, there sure is a difference in the result. I don't think we have enough data to declare victory and say GA is always better than GI. I think the data says there's, the jury's out on that. The one thing that's constant here is all of the 1180s had issues, right? We've never seen anybody bring us an 1180 that doesn't have red type B cracks. But yeah, I can't say anything about the coating yet. Insufficient data.
Okay, I think that addresses the second question, which the commenter indicated that some studies have shown that GA coatings show a lot less LME susceptibility compared to GI. I think you've basically stated that we have inconclusive data. Not enough testing was done for us to be able to determine that. Would you concur?
Right. If you looked at these two green GIs, and that's all the data that you had of GI, and you compared that to GA, you'd say the opposite would be true. I'd rather have GI than GA. But if all you had was to compare was material F versus the GA, you'd say, oh, I want GA definitely. And you would, you don't have enough data to really make a conclusion like that. But that's up to others to say,
all right?
Right? It probably needs to be a steel maker to study that, to know that the substrate is the same. You just changed the coating.
All right, switching gears a little bit. Next question was, were the welds done according to the AWS standard?
No. AWS standard would never guide you to overweld to the extent that we're doing here, okay? They wouldn't give you that cap geometry. The cap geometry is a 6 millimeter face that has a contour radius on it of 40 millimeters. Yeah, the normal procedures don't push you in that direction, but the cap geometry is the industry standard. It's not from AWS or ISO necessarily, but it's what everybody's using. So we thought that was relevant.
All right. Were the number of cracks included in this study?
No, but all the pictures are in the report. So when you get a report, you'll have, let's say it's this steel F. Every weld in that report will have at least 2 pictures of it. You'll have this cross section, but you'll also have an external view before it was sectioned of any cracks, because we document each and every weld that way. I don't know if that does that answer the question, or am I leaving something out?
I basically had provided a written response saying that in our study we did not summarize the total number of cracks that we have seen, but we do have another LME study being done in a different task where we actually do summarize the number of cracks we observe. It does factor into what we call a cracking index, but not in this particular study.
Right. Right. What we do preserve is the visual external view of the weld, so you can count different types of cracks. But unfortunately, when you do a cross section like I'm showing here, you have to choose from the external view, looking at the weld, what plane you're going to section. And once you've done that, you're not going to be able to measure crack depths in any other plane because you've kind of destroyed the part. But sometimes you will get, like in this case here, you've got a type A and you got a type B. We tended to record the type B if it occurred. That has precedence over the type A. But lately we've been recording. We would record this with two peaks. There would be a blue peak and a red peak at that amperage level. So you can certainly do that. I leave that up to others to decide how to proceed. But type B is the one that we really want to turn off. So that's what I go to first.
All right, we're going to stick with cracks here. The question, the commentator actually said, both type A and type D cracks are located within the weld indentation and considered as okay cracks. So what is the significance to distinguish between type A and type D cracks?
What was the first thing you said? I don't think they're both under the electrode.
Yeah, actually that was the comment. They're both located within the weld indentation.
No, they're not. Type B is away from the weld indentation. Okay, so if you look at this one, for example, you can see that the electrode parts and moves. It's not touching this location. This is in the plane of the original sheet material. It's right near the edge, but it's not actually touching.
So it's safe to say that A is under the indentation, B is in that transition between where the spot weld cone moving up into the shoulders, and then type D is actually away from the electrode?
No, it's the other way around. Type D came later. Where is it? Here we go. Here's the crack map.
There we go.
If it's under the electrode, anywhere from this dotted line to this dotted line, that's the electrode diameter, face diameter, that's a type A. If it's outside of the any amount of imprint from the electrode during the indentation, the amount of contact with the electrode grows, and this is as big as it gets, wherever that is. But if you're outside of that, that's type B. If you're within that transition between electrode face and this outer transition point, then it's type D. So where's the score sheet there? There we go. So here's your accept reject criteria for running this test. As far as trying to correlate back to Gleeble results, if you're seeing type A results, that corresponds with that high temperature bubble that we saw in the Gleeble results. Type B is the lower temperature stuff that is the one that we saw with the third gen steels. Type C, I'm not saying a lot about that because we're not trying to create that in this test. But we do see type D, which is in between type A and B. Sorry that it doesn't fall neatly in the alphabet. Type D is not between type A and type B, but in reality it is. It's in this space in between the type A location and the type B location. In between is D. It's just the next letter of the alphabet. And if I was doing this again, and I might create type E, which is that that radial crack that I showed you. Where is it? Yeah. When you start seeing these spiders going out, I would call that an extremely low temperature crack, which is not the same mechanism as type B necessarily. That might be a different thing going on there, and not associated with indentation, but maybe it's associated with solidification and cooling. This whole material has hoop strain in it when it cools down, and if that crack suddenly decides to grow a leg and go sideways, that's really another crack mechanism. So maybe call that type B. I don't know. I'm retiring, so somebody else gets to decide that. How are we doing on time?
Also staying with, we're pretty much at the hour, but I think we have a couple more minutes. And just to, because of time considerations, I will mention that those questions that are regards to chemistry or microstructural changes within the steel, this study did not include that length scale, meaning we did not involve chemistry, nor did we involve any microstructural evaluations as part of the study. It was simply more of a focus on the joining process itself. We do have another question on cracks here I thought I would throw at you. Which was, I just lost it because I just moved up here. Hold on a second here. Well, actually, let's just go to this question. How do you quantify the cool time between heat pulses?
Oh, that was done very carefully, always keeping an eye on the Gleeble results. Okay, we know that when we are, where'd it go? There. The ratio between the heating time and the cooling time affects the ability to suppress expulsion. It affects the ability to regulate the control of temperature in the type B location. So that was very carefully looked at and empirically correlated back to the Gleeble results. And if we mess with any of those parameters that are in the procedure, there's a good chance that you'll inadvertently throw off the correlation, and maybe you'll turn off the cracking mechanism. Maybe you'll make it worse. I don't know, but you're going to start having correlation problems with data that others might collect and data that you might go back to the Gleeble test and want to confirm. You might have correlation problems. So I wouldn't tweak any of those parameters. Just run it verbatim.
All right. So, question to you, Tracy. Do we have enough time to answer a few more questions?
Yes, I believe we have a few more minutes. Yes.
So, Tracy, could you please comment on how the attendees will be able to access this presentation after the webinar is concluded?
Yes. They will be able to go to autosteel.org, and we will have the webinar and the deliverables posted there sometime tomorrow.
Fantastic. So one last question for you, Mike, that I could find here that has not quite been addressed here, and this is back to the Gleeble test. Did you have any zinc pollution inside the Gleeble device due to the use of a zinc-coated specimen?
Was that zinc pollution?
Yes, zinc pollution.
Yes. You're fighting evaporation. Before the zinc boils away, it begins to evaporate at a pretty good rate once you're above about 800 C. The boiling point's 900 something. But you know, boiling point is just when vapor pressure is 1 atmosphere. There's plenty of vapor pressure below the boiling point. You can increase the evaporation of water if you get it anywhere near the boiling point. You don't actually have to boil it away. So that kind of evaporation is going on when you do a Gleeble test. There is, where's the Gleeble sample? There. Okay, you can see the kind of a fog around this sample. That's zinc vapors coming off of the sample. So the timing of doing this is critical. This one that is glowing so nicely is overheated. It was probably 900 or 1,000 or something, and you can see that on the samples here, if they're discolored and dark like that, there's either oxidation or total zinc evaporation. So in the Gleeble test, when you get above 900, there is no LME anymore. So some people maybe got falsely confident that said, well, LME mechanism shuts down when you get up to 1,000 or whatever. Well, the zinc's gone. So that's why there's no LME there. Okay, doesn't mean that it wouldn't happen if you did something in a pressurized chamber where the atmosphere was 5 atmospheres instead of 1 atmosphere or something like that. But in any case, Gleeble is sensitive to the atmosphere, and yes, you will pollute the chamber with zinc vapors if you do enough testing.
All right, thank you, Mike. That's all the questions I'm going to throw at you this morning. For those questions that were asked that we might not have gotten to, we do have a copy of those questions, and we will answer those after the webinar has been concluded here. So I'll turn it back to you, Mike and Tracy, for concluding the webinar.
And remember these contact names for questions that you maybe haven't thought of yet and you want to get them answered. Talk to Kevin and Hassan primarily.
So Eric, this is Mike Davenport with the Auto Steel Partnership. Real quick, we'd like to thank Mike Karagoulis for coming on and doing this. Congratulate him on his 39 years of service at GM and wish him good luck in retirement.
Thank you.
So one last thing, like Eric said, the webinar will be available online. Give Tracy a little while to get that download and everything going. And we'll also post the procedure that Mike talked about. And we'd welcome anyone out there who's doing independent work, especially utilizing that procedure. Feel free to funnel those results back to the Auto Steel Partnership. And if we get enough of them, maybe we can put a compilation together of what's being done in the industry.
That's great. The procedure is up to revision 2.0 right now. So as we get feedback from folks, if something's not crystal clear, we update the rev level.
So thank you everyone for joining us today, and the recordings will be available and other downloads within 24 hours. Thank you so much.